Hi, welcome to Mr. Wilczewski's lecture on chemical bonds. There are multiple sections to this lesson. There are 6 different sessions, and some of those sessions are divided into subsessions. So first is Introduction to Bonding. Number 2 is Bond Energy and Covalent Bond Strength. Number 3 is more about ionic compounds. Number 4 is comparing ionic and molecular compounds. Number 5 is polyatomic ions. And section 6 is bonding. Okay, section 1, Introduction to Bonding, has sections A through H. A is bonding basics. B is electron transfer and formation of ionic bonds. C is electron sharing and the formation of covalent bonds. D will talk about Lewis dot structures. And E will talk about resonance. F, what is a molecule? G, we'll talk about the polarity in molecules. And H, bond type determination. Is it ionic or covalent? Alright, so let's start with 1A, bonding basics. Okay, elements form compounds in a number of different ways. The first 2 ways we're going to look at is by sharing electrons or transferring electrons. So when electrons are shared, we call it a covalent bond. When electrons are transferred, they form an ionic bond. And there are 2 other types, main types, that we'll talk about later, and that's metallic bonds and covalent networks. Okay, elements form compounds by sharing or transferring electrons. The electrons that are involved in bonding are called valence electrons. Now, a chemical bond exists because of a balance of forces. Now, there's a mutual electrical attraction between the nuclei and the valence electrons of the adjacent atom. All right, that's a positive-negative attraction. The nuclei is positive, the electrons are negative, there's an attraction there. So this diagram depicts it. You've got a positive nuclei, and there's an attraction between that nuclei and the negative electrons of an adjacent atom. There are also repulsion forces involved in here, that the positive nuclei is repelled from the adjacent positive nuclei, and the negative electrons are repelled from the electrons in the adjacent atom. So when the forces of attraction are greater than the sum of the forces that are repelling these two, then a chemical bond can form. Okay, so when a stable chemical bond forms, the potential energy of the atoms decreases. So here, this graph depicts the potential energy on this axis, on the y-axis. On the x-axis is the distance between the nuclei. So for A, you can see the atoms are pretty far apart. They're so far apart, in fact, that there's no potential energy of attraction between them. As we get closer to the y-axis in section B, you can see the atoms are closer together, and now there is an attraction between the 2 atoms that are pulling them together. When you get down to C, that is where you have the optimal amount of attraction. In this case, it's 75 picometers between them. That's the distance between the hydrogen nuclei. And if you were to get any closer, then the energy becomes unfavorable. The key thing to note here is that the bonds form when you have the lowest potential energy. So, and that all relates to the distance between the atoms. So this is the optimal distance between atoms where you have the lowest potential energy. If they were to get any closer, all right, you would rise up this curve and you'd have it would be a less stable situation. Okay, when a stable chemical bond forms, the potential energy of the atom decreases. And there's a just larger graph. Okay, the octet rule is very important in forming bonds. We looked at, in previous lesson, we looked at the electron configurations, in particular the noble gases. The noble gases have a full S&P level, We call that an octet, except for helium, of course, which just has 2 electrons in the 1s level. This is a very stable arrangement. Those s and p's being full means the atom is not going to react with anything, practically. Now, other atoms can look like noble gases by filling in their outermost s and p orbitals by the 2 methods we just talked about, by sharing electrons or transferring electrons. So they can become more stable by filling up their s and p orbitals. So such bond formation follows the octet rule. The chemical compounds tend to form so that each atom, by gaining, sharing, which means losing or gaining, has an octet of electrons in the highest energy level. Okay, so it's very important for you to be able to, just like that, describe the outer shell electrons of an element in order to predict what it's going to do. So we worked on this before, where we asked you to be able to recognize, identify, and reproduce and develop and use the model of electron configuration in the periodic table. So hopefully you remember that everything, like in the first family, for example, has a S1 electron. And the energy level corresponds to the row, 1, 2, 3, 4, 5, 6, and 7. Everything over here, well, in the second family we'll do first, is S2s. Then we jump over here to the other side. You've got S2s, P1s in this family under boron. Then S2, P2s in the family under carbon. S2, P3s under nitrogen. S2, P4s under oxygen. S2, P5 under fluorine. And the noble gases, except for hydrogen, helium, right, have S2, P6 all the way down. Then in the middle of the periodic table, this transition area where you have the transition elements, you have the 3D. In the 4th row, you have the 3D filling up. In the 5th row, you have the 4D. Then in the 6th row, you have the 4F filling up first, and then the 5Ds, and then, of course, back to the Ps. And in the 7th level, after the S's, you have the 5F filling up, followed by the 6Ds. All right, if you don't understand this, or this doesn't make sense, review the 2 chapters, one on electrons and the other one on the periodic table. All right? But given the periodic table, any one of these elements, you should be able to look at its position and tell me, if it's not an exception, tell me the ground state electron configuration. All right? There's a larger version of the same thing. All right. Also, it's helpful, actually required, that you be able to tell me the Lewis dot notations of any element in the periodic table, and the patterns that follow are first family 1 electron, second family 2 electrons. We do not do dot notations for these transitions and intertransitions. Then 3, 4, 5, 6, 7, and 8, of course, except for helium. All right. So if you can do that, then you'll be able to understand this chapter and figure out how elements come together to make compounds. Okay, so let's take a look at this. Nitrogen. From the position in the nitrogen in the periodic table, you should be able to tell that nitrogen has this electron configuration: 1s2, 2s2, 2p3. Again, if this is not familiar to you, then please review this section on electrons and the chapter on the periodic table. All right, so how many more electrons does it take to satisfy the octet rule? Right now, we're just looking at the outermost S and P, so 2s2, 2p3, that's 5 electrons. Magic number is 8. Right? So it would need 3 more electrons to satisfy the octet rule. And what's the Lewis dot notation? The Lewis dot notation is this: 2 dots on one side, then each of the remaining 3 have 1 dot. This tells you how it's going to bond. So, and if you remember right, we told you where the dots go, the relative positions of where the dots go is important. So this nitrogen here needs 3 more electrons. So if it could form a bond over here on this side with an element and share an electron, and then do that again over here, then again over here, then it would have gained 3 electrons or shared 3 electrons. And then that tells you what nitrogen is going to do when it bonds. Let's take a look at hydrogen. Hydrogen's electron configuration is 1s1. It has one dot in its Lewis structure, so that tells you what it's going to do. It's going to try and fill up that 1s level. So it has 1s2 electrons, and there's a number of ways you can do that. We'll show you that not too long further in this PowerPoint. All right, so you can tell that it needs to gain 1 electron. Okay, hydrogen can also lose 1 electron and form an ion, but that's for later on. Okay, helium has a filled 1s shell, so it's done. It doesn't need to do anything. Okay, let's move right along. In the second row of the periodic table, lithium, configuration 1s2, 2s1. It has 1 electron in its outer shell. What does it need to do? Well, if it lost the 1 electron, then it would have the noble gas configuration 1s2. So and that's what it's most likely to do. To fill up a second level, it would have to gain 7 electrons. What's easier, lose 1 or gain 7? Might lose 1. Atoms are going to do what's easier. Remember, lowest energy seems to be a theme in nature. All right. Beryllium. Beryllium is 1s2, 2s2. So it's going to lose 2 electrons. It would be the easiest way for it to get a noble gas configuration. Alrighty then. Okay, boron. Boron, configuration 2s2, 2p1 in the outer shell. That means it has 3 electrons. It's going to be likely to lose those 3 electrons. Or we could get into sharing later on. Okay, carbon, right in the middle, has 4 electrons. It typically would gain 4 more. Nitrogen, that we talked about this, has 5 electrons, so it would be most likely to gain 3 more electrons. 1 in each side here. 1 here, 1 here, 1 at the bottom. Okay, oxygen has 6 electrons. Configuration 1s2, 2s2, 2p4. It has 6 electrons, so it would gain 2 to form an octet. Fluorine, with the configuration of 2s2, 2p5 in the outer shell, it needs to gain 1 electron. All right, so knowing the electron configurations and the position of something in the periodic table and figuring out the Lewis dot structures from that and following the octet rule will tell you what the elements are likely to do when they form compounds. Neon. Neon is the role model in this group. It has a filled S and P level, 2s2, 2p6. It's a noble gas, and it is done. It doesn't do anything, practically. There are exceptions to some of these noble gases, but that's not the subject for this course. Okay, so this you might see something like this, for example, on a test question. Electron configuration of oxygen is 1s2, 2s2, 2p4. Oxygen needs blank more electrons to satisfy the octet rule. Well, it has 6. Octet means 8. Where are the 6, you say? Well, you say you see more. Well, don't count these here. It's outermost S and P. So it's just here, 2s2, 2p4. 2 and 4 is 6. So to get 8, it would need 2 more electrons. Okay, carbon has a configuration 2s2, 2p2. Carbon needs how many? Take a guess. See if you're right. 4 more electrons to satisfy the octet rule. Nitrogen, 2s2, 2p3. It has 5. It needs 3 more to get 8. Okay. So elements form compounds by sharing or transferring electrons. When they share electrons, they form a covalent bond. We'll talk about that soon. And when they transfer, they form an ionic bond. Okay. And there's metallic and covalent bonds for later on in the chapter. Okay, so that is the end of section 1A.